Chapter 4, The States of Matter, Lesson 1, Matter. On page 102 in your textbook, I'm looking at the left-hand corner, and we're going to look at the objectives for today's lesson. Students will recognize that matter is made of particles in constant motion, and students will relate the three states of matter to the arrangement of particles within them. Although there aren't three states of matter, there's actually 4 states of matter, which we'll read about and learn about a little bit more in our lesson today. Let's get started. What is matter? Take a look at the beautiful scene in figure 1. What do you see? Perhaps you notice that water and ice. Maybe you are struck by the sun in the background. All these images show examples of matter. Matter is anything that takes up space and has mass. Matter doesn't have to be visible. Even air is matter. States of matter. All matter is made up of tiny particles such as atoms, molecules, or ions. Each particle attracts other particles. In other words, each particle pulls other particles toward itself. These particles also are constantly moving. The motion of the particles and the strength of the traction between the particles determines the material's state of matter. Reading check. What determines the material state of matter? Well, in the previous sentence before it, the motion of particles and the strength of attraction between those particles determines that material state of matter. There are 3 familiar states of matter, one that's a little less familiar. The 3 familiar states are solid, liquid, and gas. A 4th state of matter, known as plasma, occurs at extremely high temperatures. Plasma is found in stars, in lightning, and neon lights. Although plasma is common in the universe, it is not common on Earth. For that reason, this chapter will focus only on the 3 states of matter that are common on Earth. Matter is anything that takes up space and has mass. Matter is composed of tiny particles. There are 3 usual states of matter: solid, liquid, and gas. Plasma is that 4th state that occurs only at very high temperatures and is not very common on Earth. Solids, page 103. What makes a substance a solid? Think about some familiar solids. Chairs, floors, rocks, or ice cubes are a few examples of matter in the solid state. What properties do all solids share? A solid is a matter with a definite shape and volume. For example, when you pick up a rock from the ground and place it in the bucket, it doesn't change shape or size. A solid does not take the shape of a container in which it is placed. This is because the particles of a solid are packed closely together as shown in figure 2. They are actually so close together that they're forming the shape all on their own. Particles in motion. The particles that make up all types of matter are in constant motion. Does this mean that the particles in a solid are moving too? Although you can't see them, a solid's particles are vibrating in place. The particles do not have enough energy to move out of their fixed positions. Technically, all these particles are in constant motion. What motion do solid particles have? This fixed position or vibrating in place are how solids operate. Now there's going to be 2 different types of solids that we're going to learn about, and the properties of how these particles are put together in the solid kind of shows what that solid is made up of and the different ways in which the solid might react or be used in the world. Crystalline solids. In some solids, the particles are arranged in a repeating 3-dimensional pattern called a crystal. These solids are called crystalline solids. In figure 3, you can see the arrangement of particles in a crystal of sodium chloride, which is table salt. The particles in the crystal are arranged in the shape of a cube. Diamond, another crystalline solid, is made entirely of carbon atoms that forms crystals that look like pyramids. Sugar, sand, and snow are other crystalline solids. An amorphous solid, on page 104. An amorphous solid. Some solids come together without forming any type of crystalline structure. These solids often consist of large particles that are not arranged in any type of repeating pattern. Instead, these particles are found in a random arrangement. These solids are called amorphous solids, such as rubber, plastic, and glass are examples of this amorphous solid. Solids have a definite shape and volume because particles are packed closely together and merely vibrate in place. Solids in which particles are arranged in a repeating pattern are called crystalline solids. Amorphous solids have a random arrangement of particles. Here's a picture to show the difference between those 2. In our reading check, it says, how is crystalline solid different from an amorphous solid? This would kind of show what that looks like. Crystalline solids have this definite repeating pattern where they're going to have the same type of structure all throughout. They're fitting together in this nice, neat, even way, where amorphous particles are actually just really closely grouped together, but they're kind of like in this random assortment. I would compare this to how you would maybe see like tiles organized on the floor or tiles on the wall, and this is kind of like a ball pit at a McDonald's or a Burger King where all those things are just grouped together. They're kind of sitting in there in any which way. They're kind of moving around a little bit. Solids that are crystalline have this exact structure. Solids that are amorphous have this kind of spread out or loose grouping. They're still close together to form a solid, but they're not in any definite shape or pattern. Liquids. From the orange juice you drink with breakfast to the water you use to brush your teeth at night, matter in the liquid state is familiar to you. How would you describe the characteristics of a liquid? Is it hard like a solid? Does it keep its shape? A liquid is matter that has a definite volume but no definite shape. When you pour a liquid from one container to another, the liquid takes the shape of the container. The volume of a liquid, however, is the same no matter what the shape of the container. If you pour 50 milliliters of juice from a carton into a pitcher, the pitcher will contain 50 milliliters of juice. If you then pour the same juice into a glass, its shape will change, but its volume will not. Liquids are free to move. The reason that a liquid can have different shapes is because the particles in a liquid move more freely, as shown in Figure 4, than the particles in a solid. These particles in a liquid have enough energy to move out of their fixed positions, but not enough to move far apart. Liquids are matter with a definite volume, but no definite shape. If a liquid's particles move more freely than those of a solid. Viscosity, top of page 105. Viscosity. Do all liquids flow from the way water flows? You know that honey flows more slowly than water, and you've probably heard the phrase, as slow as molasses. Some liquids flow more easily than others. A liquid's resistance to flow is known as the liquid's viscosity. Honey has a high viscosity, so if it flows really, really slow, that means it has a high viscosity. It's viscous. Its viscosity, the slower the liquid flows, the higher its viscosity is. The viscosity results from the strength of the attraction between the particles of the liquid. For many liquids, viscosity increases as the liquid becomes colder. For example, with breakfast this morning, Mr. Shane had pancakes and some syrup. If that syrup is kept in the fridge, it actually slows down a whole bunch and it becomes more viscous, as in the syrup moves really, really slowly. If that syrup is left out at room temperature, it actually moves quite a bit faster. If it's hot syrup, as soon as it gets on those hot pancakes and it moves a lot faster, its viscosity has lowered. So viscosity is a liquid's resistance to flow and increases when particles are more strongly attached to each other. Let's take a look at a real-life example of viscosity. Remember, viscosity is how fast or how slow a liquid is able to move based on the properties or what that liquid is composed of. Something has a high viscosity if it moves really, really slow, like it's in slow motion. You get it. Something that has a low viscosity, something that moves really, really fast. For example, we've got this wonderful coffee creamer that Mr. Shane had in his coffee this morning. It moves relatively quickly. You can see how fast it goes from one spot to another as that liquid fills its container. Another example is something that moves a little bit slower because it's got a higher viscosity. It's thicker overall. It doesn't have that same type of movement that the bottle has in comparison to your coffee creamer. Another really good way to show this viscosity is actually to have a race between two different types of liquid material. And this is often a question people ask about what they're going to put on a burger or maybe a hot dog. What's your favorite condiment? Well, we've got two of those options here, ketchup or mustard. I'm going to spray both of these on the board, make this big, huge mess in class today. We're going to see which one is more viscous. The higher viscosity will actually be the one that goes slower. The lower viscosity is actually the one that moves faster. Let's see who wins. Ketchup and mustard. Make your choice, make your prediction. Who do you think is going to win? And ready, set, go. It looks like we're off to a really heavy, substantial lead for ketchup. They're coming around the last bend, and ketchup is still having a substantial lead increase. Maybe if we give mustard a little extra persuasion, they're going to want to move. Go, 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 go. Nope, just going to pile up there, look all really gross. Moving faster. Is ketchup coming to the finish line really, really closely? All right, you can see it. Maybe we don't have to wait all day long for ketchup to finish the race. But ketchup is winning. Ketchup is winning. Ketchup is winning. That means in this example, we've got mustard with a higher viscosity, meaning it doesn't want to move whatsoever. And we've got ketchup coming to the finish line having a lower viscosity because it's flowing a lot easier. Difference between how those liquids behave is a lot of times based on those properties. And the winner is ketchup. Woo! The crowd goes, wow. Thanks for tuning in. Surface tension. If you're careful, you can float a needle on the surface of water. This is because attractive forces cause the particles on the surface of a liquid to pull themselves together and resist being pulled apart. You can see in figure 5 that particles beneath the surface of liquid are pulled in all directions. Particles at the surface of liquid are pulled toward the center of the liquid and sideways along the surface. No liquid particles are located above to pull on them. The uneven forces acting on the particles on the surface of the liquid are called surface tension. Surface tension causes the liquid to act as if a thin film were stretched across its surface. As a result, you can float a needle on the surface of water. For the same reason, the water spider can move on the surface of a pond or a lake. When a liquid is present in small amounts, surface tension causes the liquid to form small droplets. To better understand surface tension, it's really good to visualize how this works. Again, surface tension are the uneven forces acting on particles on the surface of a liquid to cause the liquid to attract to itself. Here's an example of what that looks like on the surface of a liquid. Inside the liquid, all the water particles, all the water molecules actually have even attracted to each other because of the way in which hydrogen bonding works, which these particles are attracted because of polarity. There's a positive and negative charge between those particles that hold them together with that attractive force. But on the surface, there is not the same type of water above as there is below, so the surface has a different level of attractive forces on one side of it. There's more attraction here than there is on the top. Hence why a needle can float on the surface of the water, because there's this tension that exists on that actual surface. Another example of how this shows up is when water forms a droplet. Water has this tension on the surface where it's attracted more to itself than it is on other things. So as it's being poured out, it's going to form this droplet where it's being attracted to or attached to itself. This happens in the form of like a water droplet that looks like this, and also happens in the form of like how water kind of beads up on any type of solid surface, like on the outside of your car, or if there's condensation on, like, say, a bottle of soda or on a glass, it beads up and it sticks to itself. Another maybe not so good example is the example of our Lord and Savior Jesus using surface tension to walk on water. Just kidding, he didn't use surface tension to walk on water, but you can imagine those attractive forces helped him a little bit, even though he used his omnipotence, his all-powerness as God to perform this miracle. Peter was able, actually, because of Jesus, to do the same thing until he lost faith and didn't focus on what he was supposed to be focused on, and then sank in and gave us the real example of how surface tension works when something is too heavy on it. When something's not too heavy, though, like when water bugs walk on water, they have this ability, because they're so light, to not break through that surface tension. So surface tension is a powerful attractive force, but not powerful enough to where you and I aren't going to go like Peter crashing into the water. Jesus walks on water not because of surface tension, because he's God completely and has that ability to kind of break the rules of what we would understand as science and physics in the world. Last portion that we're going to read through today is on page 106. Gases. Unlike solids and liquids, most gases are invisible. The air you breathe is a mixture of gases. The gas in the airbags in figure 6 and the helium in some balloons are example of gases. Gas is matter that does not have a definite shape or volume. The particles in gas are much farther apart than those in a liquid or solid. Gas particles move at high speeds in all directions. They will spread out evenly as far apart as possible. If you poured a small volume of a liquid into a container, the liquid would stay in the bottom of the container. However, if you poured the same volume of gas into a container, the gas would fill the entire container completely. A gas can expand or be compressed. Decreasing the volume of the container squeezes the gas particles closer together. Vapor. Matter that exists in a gas state but is generally a liquid or solid at room temperature is called vapor. Water, for example, is a liquid at room temperature. Thus, water vapor is the term for the gas state of water. Gases are matter that do not have a definite shape or volume. Gas particles, based on the ideal gas law, actually spread out to completely fill their container, because those particles have such high level of energy, they're constantly moving throughout that entire space. Anytime that there's a solid or a liquid at room temperature that's heated up and it turns into a gas, for example, when you boil water, it turns into steam, we call that thing a vapor. Water is probably the best example to understand what that normal room temperature item that exists at a solid or liquid state turns into a gas, because of that introduction of heat and more energy into that circumstance. That wraps up our study of those three major parts of matter: solid, liquid, and gas. If you'd like to learn more about plasma, I'm going to post an extra video that talks about how it's actually the most prevalently existing item in our universe, but it's not as popular and it's not as prevalent here on Earth. God's blessings with your reinforcement assignment.